Welcome back to the workshop. We want to continue taking a look at section 3.2, which is probability distributions, and we want to consider a theorem regarding the probability distribution. So let's take a look at our notes. So a function can serve as the probability distribution of a discrete random variable if and only if that function f of x satisfies two conditions. First of all, that f of x is greater than or equal to 0. Of course, because the probabilities have to be greater than or equal to 0. Additionally, the sum of the probabilities has to be equal to 1. And of course, that makes sense as well, because this should account for all, right, let's see, use the right language here. Our random variable is a function that is defined on all of the sample space. So when we consider a sum of the probabilities for all possible outcomes, right? Because this f of x is the various outputs for the random variable, and then every element in the sample space, every outcome in the sample space has a value for the random variable. So when we consider all possible values of the random variable, we're considering all possible outcomes, which is the sample space. So the sum of the probabilities over the entire sample space should be equal to 1, right? These are essentially identifying with the postulates for probability. All right, so let's think of this theorem and decide if these two functions can be used as a probability distribution for some discrete random variable. All right. So of course we can notice that it's discrete because our possible x values are 1, 2, 3, and 4. That's it. So this makes sense at least a little bit here to begin with, but then we of course need to double check the two conditions, that the individual probabilities, the individual function values are greater than 0 or equal to, and that the sum of all the probabilities is equal to 1. So let's investigate these individual conditions. All right. So f of 1 is equal to 1 squared plus 1 is 2, so it's 2/35. F of 2 is equal to, well, and of course, what we want to notice about that is that it is greater than 0. F of 2 is equal to 2 squared plus 1 is 5. 5 divided by 35 is 1/7, which is greater than 0. F of 3 is equal to 3 squared plus 1 is 10. 10 divided by 35 is 2/7, which is greater than 0. F of 4 is equal to 4 squared plus 1 is 17. 17 divided by 35 is 17/35. Excellent, which of course is still greater than 0. So we have condition 1 satisfied. Now we want to consider the sum of the function values over all possible outputs or all possible values of the discrete random variable. So that's just saying, all right, well, what's f of 1 plus f of 2 plus f of 3 plus f of 4? And we already calculated these, right? That's 2/35 plus 5/35 plus 10/35 plus 17/35. Now 2 plus 5 plus 10 is 17. 17 plus 17 is 34. 34/35 is not equal to 1. So no, f of x may not be used as a probability distribution for a discrete random variable. Easy enough. All right. What about this function? All right, now this one is a little bit different. The possible values for the discrete random variable are 1, 2, 3, 4, and so on. It continues on forever. Okay, so if this is the case, right, there's an infinite number of values, so that's a little bit interesting. So instead of checking all of the values, because we could never do that, we should notice that if we were to plug in an integer such as this, then we would get 1 over 2 to the k, which is, of course, greater than or equal, well, it's strictly greater than 0. So that's for all k greater than or equal to 1. So that first condition, that they're all positive or non-negative rather, is satisfied. Excellent. Now we just have to observe if the sum over all possible x values, if that is equal to 1. So this is a little bit interesting here. We got to have a little bit of fun with our summation notation, kind of reaching back into, let's see here, calculus 1 a little bit, as well as calculus 2. I think more calculus 2 in this case. Okay. So this is because x goes on forever, right? We're looking at an infinite sum or an infinite series rather. So we have right? There's no ending. We don't eventually stop. So this is the sum from I equals 1 to infinity of 1 over 2 to the I. And this looks pretty good. Pretty good. But how do I find that sum? Well, this looks really similar to a geometric sequence, but when it comes to a geometric sequence, we actually need to have I starting at 0 in order to use the typical formula for the sum of a geometric sequence. So in order to get it to start at 0, what I'm going to do is I'm actually going to observe that I could pull out a factor of 1/2. Let's see here. And that would give us the sum from I equals 1 to infinity of 1 over 2 to the I minus 1. But now when I start at I equals 1, that would be starting at 0. Okay, so when I plug in 1, I get 2 to the 0. That's perfect. So I can adjust my index here, my indices, so that way I've got 1/2 times the sum from, let's call it k now, so we can focus on that change. Of course, when I drop it down 1, it's still going to go off to infinity, and it becomes 1 over 2 to the k. Excellent. This, I can use the formula for the sum of a geometric series, so I have 1/2 times 1 over 1 minus 1/2. Of course, 1 minus 1/2 is 1/2. 1 divided by 1/2 is 2. 1/2 of 2 is 1. Bam. So the second condition is satisfied. Excellent. So an infinite sum, we still end up with a finite value, and that finite value is exactly 1. So yes, f of x may be used as the probability distribution for some discrete random variable. Excellent. So that's just what we wanted to focus on there. So we have a little bit about probability distributions. All right, that's all that I have for this video. So I'll see you guys again soon back here in the workshop.